This is Project 1, Video 1, the video where I do the pencil and paper part of the project. So let's take a look at project requirements. We've got a set of particles, each having a charge of 100 microcoulombs, distributed along the y-axis of a Cartesian coordinate system from -25 millimeters up to 25 millimeters. And we got to write two octave functions. One function that takes one argument, namely a value of x, and returns the x component of the electric field at the point on the x-axis having that value of x. So find E of x. It's really E sub x of x. And then one that graphs it. Okay, let's work on the first one. We need a coordinate system. Y-axis, x-axis. We got a bunch of charged particles distributed along it. I'm not going to try to draw all of them, but rather give the idea. And each one of them makes a contribution to the electric field at some point on the x-axis. I'll call it point P. So for instance, this one right here, I'll call it particle number I, makes a contribution to the electric field at point P. It's a positively charged particle, so it'll be directly away from that charged particle, like this, E sub I. And the magnitude of E sub I is going to be given by charge of the particle. Well, be given by our expression from Coulomb's law for the electric field. So K E is equal to K Q sub I. I'll call it E sub I. I already did call it E sub I, so I'll stick with that. Q is the charge of every single one, so I don't really need to put a subscript on it. KQ over R sub I squared. And R sub I squared, this will be the distance R sub I this will be the distance, I'll call it x. Every point is the same distance x. Well, every charged particle that's contributing to the electric field at point P is a distance x away from the origin, where x represents the distance to point P. And then the distance that this charged particle is away from the origin is its value of y. It's actually the distance is the absolute value of y. So for the charged particle that I've chosen to work on, like the one I labeled I, the distance is a positive value, but the y coordinate of that particle is negative. Let's see, we can express R sub I from the triangle up there as the square root of x squared plus y sub I squared. I don't have to worry about it being the absolute value of it because I'm squaring it, so I'm going to get a positive value anyway. So E sub I is, I think I'll leave it like that. Yeah. So to get E sub I, I have to calculate what R sub I is on the computer, and then I have to plug that in there. And then EI X component is going to be equal to EI times the cosine of theta. So for that, I'm supposed to have a vector component diagram. There's EI. There's theta. EI X component. EI Y component. I should point out that for every charged particle that we have down below the origin, there's going to be a corresponding one up above the origin with the electric field in a direction away from that charged particle, so it'll be down and to the right, whereas this one was up and to the right. And it'll be the same distance, so it'll have the same magnitude, and that means it's going to have the same magnitude of the Y component. But this one's got a positive Y component, the one that I showed, and the other one would have a negative Y component, so those will cancel out. So the Y components of the electric fields due to all these charged particles cancel out pairwise. And I just noticed something. I've indicated a charged particle at the origin, which is not going to be the case, so I think I'll go ahead and get rid of that. So our distribution of charged particles is going to be one that does not have a charged particle right at the origin. Alright, so then from this we get that EIX is equal to EI cosine of theta. Alright, I think then E sub I X component, EX component, the total EX component is going to be the sum over all the charged particles of the EIX. The sum of all the EIXs. So it'll be the sum over I. If I label the bottommost one number 1, so and then the topmost one I could label, there are going to be 26 of them. So I could call that I is equal to 1 up to I is equal to 26. The sum over all these charged particles. Alright, so I think I'm ready to start outlining the code. So given X, so given X, so I'm going to write a function, and I got to come up with a name for it. I think I'll call it get EX. Yeah, I think I'd rather just call it EX. I just call it EX, capital EX. Its argument is X, so I think I'll leave that part out. I don't really have to do anything given that X is given to it, and I think I'll give it a return variable, E sub X. I think that's what I'll call the return variable. So I'm going to go E sub X I think I'll write it as E underscore X equals EX of X. So this is the name of the function right here that I'm going to use, and this is my return variable name. Now I'm actually going to be typing that line in. In general, this outline of the code is more or less in English what you're going to write in order to make the computer do what you want it to do. But I'm going to, in some cases, it will actually be what you're going to be typing in into Octave. Alright, so outline. Alright, I see I'm going to need a K, initialize variables. So in other words, set K equal to what it is on the formula sheet. Something like 8.9 times 10 to the minus, times 10 to the plus 9. Newton meter squared per coulomb squared, but set K equal to the value. Let's see if and Q Q equals that one I can write down here times 10 to the minus 6, and it is going to be in coulombs. I'm going to understand. I'm going to have everything in coulombs and meters, but I can't give it the units in the program. Alright, I'm going to create an array of Y values. Y equals, I'm going to make it go from minus 0.025 meters. Again, it doesn't understand the unit, so I'll leave that off. In steps of 0.002 meters, so 2 millimeters spacing, all the way up to 0.025 meters. Now what this should do is create an array of 26 values from 0.025 in steps of 0.002 up to 0.025. So for each array we got to calculate the R. So I'll just put in R is equal to square root of x squared, which we've got as the argument of the function, plus y squared. We got to do this in a way that makes it so that even though x was a single value, y has these 26 values, and it makes it so that we've got 26 values of R. So this is an array. This is an array. It's not like R is just going to have one value. It's got a set of 26 values. And then E, calculate E using that equation. KQ over R squared. And then this is an array. If I do it right, because the R's got 26 values. And then I think I want to do a little bit more work up here. Figuring out what cosine of theta is. So cosine of theta, I can say from up here, that's theta. So the cosine of theta from analyzing this triangle here is equal to R, no, I'm sorry, X, the adjacent, divided by R sub I. So, it doesn't look like an R sub I there, divided by R sub I. Alright, so with that, cosine of theta is X over R sub I. We can say that EIX EI times X over R sub I. I think I want to keep on going with that. Is that good? Yeah, so EIX is equal to, I'll go ahead and substitute the EI in there. I think I'll leave it like that. I think I'm gonna back up, then I don't have so much to substitute here. I'll calculate the cosine of theta separately. So you could combine this algebraically and make the code simpler, but I think it is more self-explanatory if I do it this way. So I think I'll calculate the cosine of theta as X over Ri. And where should I do that? I think I'll do that down here. So our next step in my outline of the function is E sub X, and that's actually going to be an array of values again, is, oh wait a second, I got to get the cosine first. Cos theta is equal to, I think I said X over R. So this is a number, and this is an array of values. So cos theta will have an array of values where each one is the cosine of the angle for the specific R. So what I call it R sub I in the analysis. So then EX is equal to E times the cosine of theta. Cos theta is what I call that. Alright, then I've got one issue. E sub X is when I get the total vector at that point, the total vector E is going to be E sub x times I hat. That'll be our total electric field vector for the electric field at any point on the x-axis. Now, what I got to worry about is that if I'm to the left here, I realize for the graph we don't have to worry about to the left, but we still want our function to be working at all points. So if point P is to the left there, the E sub x should be negative because all these are positively charged particles, so I know the total E is going to be pointing away from that. So let's see if that works out. And I actually think it does in our code, in that cosine of theta, the cosine of the actual physical angle would be the absolute value of x, but x is going to be a negative in there. So I think it's when we multiply by the cosine of theta, we're going to get the negative sign if x itself is negative. And here, as far as the r value, it's not going to mess things up because it's being squared. So it should work out automatically, but we'll test it for points to the left once we write the code. So this is what I was calling E sub x. I called that my return variable. So I think I'll use the return variable name here, so I don't have to explain that I have to assign it to the return variable. So I'll just put that as E underscore x, which is what I was calling my return variable. So this I guess we haven't done that yet. This is EX. It's an array of them, and I wanted E sub x to be something else. So I think I'll E underscore x. I think I'll put that back the way I had it. EX, and then E underscore x. So this is the x component due to each of the particles. It's an array, so it's got the answer of the E sub x for every charged particle. So I'm going to have 26 values of E sub x stored in that, and I want this to be equal to E underscore x, and I want that x at the normal level, not as a subscript. E underscore x, my return variable, is going to be the sum of all the elements of E sub x. So this is an array with 26 values. This is an array. And that represents my outline for the code. So my calculations in here, and then the outline for the code, which looks very much like the calculations there. Alright, be careful, in submitting this before you do any of the coding, because as I code it, if I find that I had a mistake in my pencil and paper part, I'll go back and fix it. So sometimes when you're actually programming it up, that's when you find a mistake in here. So I wouldn't just hopefully you're working it out on your own, but I would advise you don't want to just copy and submit this without looking at without doing the programming first, or at least watch my videos, because again, if I find a mistake, I'll come back here and correct it. Alright, that ends project 1 video number 1, the pencil and paper part.